Hello everyone, welcome to the another presentation from Turkey Java community. Today we are here. We are with Catherine Edelve from Belsoft. Welcome, Catherine. How are you?
Hello, Mustafa. Hello, everyone. I'm fine. That's perfect. I'm so happy to be here today. We're going to discuss a very, very interesting topic. So I'm looking forward to it.
Yeah, we are very excited to hear to watch your presentation also. And before that, I want to point out a few a few things, if you don't mind. As Turkey Java community, if you follow us, you know that we are mainly performing physical events mostly in Ankara and Istanbul, and we are also bringing some famous people, distinguished guests from around the world, like Catherine. So we first want to thank our sponsor DefineX, and we want all our followers. We would like their support by subscribing to our channels and liking our videos and postings. So today we have a very exciting topic. As you know, JVM is very fast, and but in the recent years, if you know, there has been some improvements to reduce the startup and warm-up times, and Catherine will now present us about these exciting topics. Um, then I also want to clarify that if you have any questions during the presentation, please write in the chat box. And after the presentation, I will direct the questions to Catherine for answering. Without further ado, then the stage is yours, Catherine.
Okay. Thank you. Thank you so much. So let me share my screen. Okay. All right. Okay. So slideshow. So here we go. Right. So as Mustafa has already said, the topic of our discussion today is reducing Java startup and warm-up times. And first, let me tell you just a couple of words about myself. My name is Catherine Edelve. I'm a developer advocate at Belsoft, and Belsoft is a major open JDK contributor and provider. The company is part of various boards and committees, including GraalVM Advisory Board and Cloud Native Computing Foundation. And the Belsoft engineers have a vast expertise in adapting and optimizing Java for the cloud. We offer a variety of solutions aimed at making your Java applications more performant and secure in the cloud. For instance, we offer Liberica Native Image Kit, which is a GraalVM Community Edition-based solution for creating native images, and we are going to discuss GraalVM Native Image today, later on. We also offer Liberica JDK, all LTS versions, versions 6 and 7, and non-LTS versions. Liberica JDK is recommended by Spring, and we offer a special flavor of Liberica JDK called Liberica JDK Lite. It comes with several enhancements, such as better module compression and backports from newer versions, and taken together with AppCDS Linux, another our product, it helps to create the smallest base image for Java applications on the market. AppCDS Linux is a lightweight Linux distribution. It is 100% Alpine compatible, but comes with numerous enhancements, including 2 libc implementations, glibc and optimized muscle. So what it actually means that when we're talking about optimizing Java for the cloud and Java performance in the cloud, we know what we talk about. So let's see what we will cover today. First, we are going to talk about how Java applications start to lay the foundations for the further talk. Then we will discuss why reducing Java startup and warm-up times actually matters to you. And then we are going to delve into 4 approaches to reducing Java startup and warm-up times. We are going to talk about application class data sharing, or AppCDS, Project Leyden, which is currently under development, GraalVM native image, and the coordinated restore checkpoint project. All right, so let's start with answering the question, how does a Java application start? This process includes 3 stages, that is the JVM start, application start, and JVM warm-up. During the JVM start, the JVM service code and data get loaded and initialized. The core JVM classes get loaded and initialized. The dependencies of the main class get initialized, and finally, the main method is invoked. And JVM start takes about several milliseconds on modern hardware, so there's actually not much to optimize, right? Then the application starts. The application classes get loaded and initialized, the dependencies get resolved, and necessary resources get loaded. And application start takes about several seconds. So there's already some room for optimization. But then a very important part comes. As you know, the Java applications are compiled just in time. So when you compile a Java file, the Java source code is turned into Java bytecode, and you get a jar file. And then at runtime, the Java bytecode get compiled into the native code. But that's only part of the deal. Another part is the JVM warm-up. So the purpose of JVM is to get highly performant code, right? So JVM is famous for its good performance. And so JVM analyzes the running code to find so-called hotspots, that is, code parts that are used most often and may require optimizations. It also determines which operating system the application runs on, and so on. And then the JVM compiles and profiles different versions of machine code to choose the most performant version. Another powerful feature of JVM is that it can dynamically recompile code in case there are any changes in the environment and the situation, and perform adaptive optimizations, right? So your code always stays performant. So the Java application starts in several seconds, and the JVM may take several minutes or even hours. Well, that actually depends on the load, because if there's no load, there's nothing to optimize. What's in it for you? Why should we care about that? Well, the thing is that mostly we deploy our applications to the cloud nowadays. And the cloud offers immense opportunities in terms of scalability, automated workflows, the management of big volumes of data. But with great power comes great responsibility. And you have to pay for the resources reserved for your application. So even if the application does nothing, if it runs idly, you still have to pay for the resources, right? One way of dealing with that problem is to implement the scale to zero approach. That is, when you scale the resources to a minimum and stop all the services when there's no incoming traffic. Then when there are requests, when the traffic comes, the resources are scaled up to meet the demand and then scaled down again. That is a very good approach that enables you to use the resources sustainably and, well, reduce cloud costs, right? Because you pay only for the resources when you actually use them. And major cloud providers offer, solutions for that, for instance, AWS Lambdas or Google Functions, to name a few. But as we already determined, it's not that simple to start a Java service, right? It doesn't start in several milliseconds, and it has to warm up, right, before it reaches peak performance and can serve all the incoming traffic, right? Another side of the problem is that JVM requires more memory during the warm-up stage, because it needs to store the profile data and the bytecode cache. So you have to allocate more memory to your cloud instances, and then when the application is at a stable state, it doesn't use these resources, but you still have to pay for them, right? So there, you overpay for the cloud, and that is a problem, right? So how can we deal with it? How can we alleviate the problem? Luckily, there are 4 solutions. 1 of them is under development, and 3 of them are production ready and, well, at your service, so to say. And these are application class data sharing, GraalVM native image, coordinated storage checkpoint, and Project Leyden. We are going to discuss them right now, one by one. All these approaches have different impacts on startup and warm-up times, and they are associated with different challenges of implementing them, if there are any, right? So I hope that after my presentation, you will experiment with all of them and choose the solution that's best fit for your purposes and for your project. Let's start with application class data sharing, because it's the simplest one to implement. So the idea behind application class data sharing is quite simple. All applications need classes for their work, and core JVM classes and application classes need to be loaded and initialized at application start. But complex applications use thousands of classes, so this process may take several seconds. But the worst part is that it is a repetitive process, right? So it has to be repeated every time the application starts. And that is where AppCDS comes into play. So it is an integral part of OpenJDK, so it is not a third-party solution. You don't have to manually install anything, right? So AppCDS reads a set of platform classes and application classes, parses them, and stores this data in an archive as a read-only metadata. And then when the application starts again, the JVM sees that there is this archive. Well, of course, if you point to it, right, with an option, it sees that there is an archive and reads the data from the archive. And reading the archive is faster than loading the classes from scratch. And so the startup is reduced. Using AppCDS is simple. You don't have to change your code in any way, right? So you have your jar file, and then you start your application. This is going to be like a trial run. You start your application with an option, archive classes at exit. And then you point to the path where the archive is going to be saved, and you can specify the name. In this case, it's application JSA, but you can give any name to it, right? My archive.jsa or something, right? And so when the application exits, the archive with the classes is created. And then when you run your application again, you use another option, which is shared archive file, and point to this archive, and then the JVM is going to read it. With AppCDS, you can achieve about 40% startup reduction. But if you use Spring for your projects, it is even better to use AppCDS with Spring AOT, so ahead of time. Spring AOT is aimed mainly at helping to create native images with GraalVM, but it can be used also with AppCDS. And Spring AOT feature generates some Java source code, bytecode, and runtime hints. And let's look at how we can use that with Spring. So if we are using Spring AOT, let's also use an exploded jar. An exploded jar is recommended by the Spring team to be used in production instead of executable jar. So first, you compile your application with the Spring Boot process AOT to enable AOT. When you create your jar file, then you use djar mode tools extract to extract the jar file from the executable jar. And then you perform a trial run like we did before. with the archive classes at exit feature, but also you enable AOT with Spring AOT enabled. And you can also, if you Spring Boot, you can use another useful option, that is Spring Context Exit on refresh. It means that when the application starts, it will exit automatically, so you don't have to do that manually. And then you point to the extracted jar file. And after that, you run your application again, well, in production. You enable AOT again and point to the shared archive. And using AppCDS with Spring AOT can yield about 50% or maybe 55% better startup, which is already better, right? You can, of course, use AppCDS in containers. So Bellsoft offers ready container images with the prepackaged CDS archive for JVM classes. And, well, the workflow is the same, right? So you run the application inside the image when it's built, and you specify that it needs to create the archive. And then when you start your containerized application, there's an entry point that says already a shared archive file. And so it's already started with the specified archive, created archive, so the startup is faster. You can also use containers, AppCDS in containers with build packs. That's even easier, right? So you don't have to write a Docker file. You just enable JVM CDS enabled option in your configuration file in Maven and Gradle. And that's it, actually. Well, to sum up AppCDS, the advantages is that you don't have to refactor your code. It is suitable for any application. There are going to be no compatibility issues, and, well, everything is just great. But the disadvantage is that it doesn't actually yield a drastic startup reduction, right? So not like 90% or something, right? Only 40 or 50. And it doesn't actually impact much the warm-up stage. And as we have already seen, and as we have already discussed, it takes, well, much longer than the actual startup. So we want to deal with that as well. Well, the next solution that we're going to discuss is GraalVM native image. It's already a more drastic solution to startup and warm time reduction. And GraalVM native image uses ahead-of-time compilation instead of just-in-time compilation, just like with traditional Java apps. So ahead-of-time compilation happens at the build time, right? So when you build your native executable, the GraalVM native image receives the Java bytecode, so that's the application, the libraries, the JDK, the JVM, and then it performs the static analysis of the code. It performs points to analysis, so it determines which classes, methods, and fields are reachable. And only these classes, methods, and fields are going to make it into the final executable. Then it can run some initializations. So it can initialize some classes which are safe to initialize, and other classes will be initialized at runtime. And then it also performs a heap snapshotting. So the objects that are created by static initializers are written onto the image heap. And then the compiler translates the Java bytecode into machine code. So it means that if you're building a native image on Linux x86, you can run it on Linux x86 only, right? So everything depends on the system and the architecture that you build your image on. As a result, you get a native executable. It's a single file that contains all necessary classes, necessary library classes, compiled code, and statically linked code from the JDK. It doesn't contain the whole JDK, right? Only the code that is necessary for the application. Well, native image, as a result, starts in milliseconds, so in under a second. And it already starts at peak performance. So there's no warm-up stage because the optimizations were already performed at compiler time, which is just great, right? There are several distributions of GraalVM. There's Oracle GraalVM, and there's GraalVM Community Edition. and two downstream versions of GraalVM Community Edition, that is Liberica Native Image Kit provided by Bellsoft and Mandrill provided by Red Hat. The key differences between them are in licensing, in the supported JDK versions, available garbage collectors, and we are going to discuss this point a little bit further on, and whether the enterprise support is available. So using GraalVM native image is also, well, not very difficult. You can, there are several ways of using it. So you can download the GraalVM distribution and use the native image tool. You're using your jar file and the native image, and then the native executable is created. You can also use the Maven plugin, right, to create a native executable. In this case, you don't need to create the jar file beforehand. It's going to be done for you. And of course, you can use Gradle for that. You can also use native image containers. So for instance, Bellsoft provides ready container images with Liberica Native Image Kit and Alpakit Muscle. So in this case, as you can see, we can build our native executable inside the container, and then we transfer it into a fresh base image with Linux only, because as I already said, it doesn't need the JDK to run. And then you point in the enter point to your executable, and that's it. And of course, native image is also available in build packs. So you just use the plugins that I mentioned earlier, a couple of slides before, and then you just use one line of code to build a native image in a container with build packs. Just super great. It's very convenient. Well, yes, the startup is super fast. The warm-up, there's no warm-up. The executable starts at peak performance. That's just great, but yeah, there's always a but, right? So when we get such benefits, obviously there's going to be something behind them, right? So the other side of the moon. So let's discuss that a little bit. There are considerations, of course. So first of all, building a native image is a very resource-demanding process. You have to allocate several gigabytes of memory to that. I don't actually see it as an obstacle, because it's only required once for building the native executable, and then you just enjoy all the perks of native image. The second point is that it takes several minutes to build the image. But again, I also don't see it as an obstacle, because you suffer once and then you enjoy the almost instant startup. But the other 2 points are quite important to consider. So native images are quite performant, but the native image offers a limited choice of garbage collectors. So there is CRaC and AppCDS in all distributions, and there is ParallelGC in Liberica Native Image Kit in addition to those. And there is G1GC in Oracle GraalVM, right? So if you're not satisfied with the overall performance of your native image, you can choose a distribution with an additional collector and try using that and see what happens. And of course, I have to mention that GraalVM native image is not the best friends with the Java dynamic features, such as reflection, dynamic proxies, and so on and so forth. This is because the static analysis, the static analysis happens under the closed world assumption. It means that everything must be reachable at compile time, so everything that application uses, or else it's going to be thrown away, right? So it's not going to get into the native executable. And well, the dynamic features of Java, well, they happen to act at runtime, right? So and they may be not noticed by the native image at compile time. It means that the native executable will be built, but it may fail in production. So what we can do about that is we have to provide the metadata about the usage of dynamic features in your application. You can do that automatically with the tracing agent. So it's not impossible, of course, but it's just an additional step that you have to perform, right? So to be able to enjoy using native images. So to sum up the GraalVM native image, The pros are that it offers drastic startup reduction, right? Immediate peak performance without warm-up, and potentially smaller images. I say potentially because it actually depends on your application, because the native code may be a little bit bigger than the bytecode, and then, as I already said, the native executable contains some already created objects. So if the application is small and quite simple, then yes, the image is going to be smaller than the image built with the traditional JDK. Otherwise, it's going to be, well, about the same size. Well, that depends. Again, that depends on your application. It's not going to be much bigger. Right, and the disadvantages is that there are challenges with Java dynamism, right? So you have to provide the metadata. The dynamic performance optimization is not possible because there is no JVM, right? And so the peak performance is going to stay the same, right? So it can't be adapted at runtime. And as I already mentioned, there's a limited choice of garbage collectors. Then the third solution, which is also production ready, it's the coordinated restore a checkpoint, or CRaC for short. It is an OpenJDK project, but it is not a canonical OpenJDK project. So it was contributed by Azul, and currently there are two OpenJDK providers, so that is Azul and Bellsoft, that offer builds of JDK with the support for CRaC. All right, and as it is not a canonical OpenJDK project, there is no TCK verification, and well, yeah. But still, you still can use it, right? So by taking the builds from one of the vendors that provide it. So what's the point of CRaC? It enables you to pause a running Java application and warmed up Java application, save it to the file as a snapshot, and then restore the application from the file from the moment it was paused. Much like with the video game, right? So you play a game, you have some achievements, you've come a long way, and then you save it. And then when you resume playing, all your achievements are still there, and you start from the exact point where you left, which is just fabulous. And the JVM is still there, so that's our familiar JVM. So it means that dynamic performance optimizations are possible after you restore the application. CRaC uses Creo, which is a Linux technology under the hood, so it is only available for Linux. So if you want to experiment with it on your local machine, you either have to have Linux installed or you have to have a virtual machine with Linux in it. But as we are dealing with containers mostly, well, Linux is there in the cloud, so there's nothing to worry about. So how do you use CRaC? In the simplest case, you use the, well, of course, you take the JDK build with CRaC support, such as, for instance, LibRJDK. Then you take your jar file, right? So you have this option, CRaC checkpoint 2, that you specify when you run your jar file. Then you tell JCMD, which is a part of OpenJDK, to perform the checkpoint. And then after that, when you want to start your application from the snapshot, you use only one option. Please notice that. So there's no jar file. You only specify the option CRaC restore from and point to the checkpointed snapshot. And then the application is going to be restored from the snapshot. You can, of course, use CRaC in containers. For instance, if you use Spring Boot offers support for CRaC, so you need to add the dependency for the CRaC project. Then you can take a ready container image with CRaC support, such as library runtime container with CRaC. You build your application in the usual way, and then you specify in the entry point this option, CRaC checkpoint 2. And as we're working with Spring in this case, you can also specify Spring context checkpoint on refresh for the application to exit automatically. It's not necessary, but well, it's convenient. And then after that, you run your image. You have to have two capabilities added. checkpoint restore and system trace for the snapshot to actually happen. And then you point to your Docker image. All right, and then after the snapshot was taken, you you transfer your application to the another image, and you change the entry point. So we had CRaC checkpoint 2, and now, as you can see, the entry point contains CRaC restore from, right? So this is when you start the Docker image, the application is going to be actually restored from this checkpoint file. And then you start the Docker image by restoring it. So again, you need checkpoint restore and system trace capabilities. And then, yeah, you just restore it, and the application starts in several milliseconds. There are, of course, considerations when using CRaC too. Just like with a native image, it offers a great startup production, no warm-up, because it already happened sometime before you took the snapshot. But as I already said, the problem is that the CRaC can be used on Linux only, but that's not the biggest problem. The biggest problem might be is that you have to possibly augment the code and add special methods, so before checkpoint and after restore, for the application to perform the checkpoint restore reliably. So the project is called coordinated, which means that the application is actually aware of the fact that it's being snapshotted, and then it can either abort the snapshot when if it deems the moment well, not quite fit for that, if it's performing some operations, or it can perform some preliminary actions like closing the connections and so on and so forth. But still, with the complex applications, you may have to also add manually some methods for your application to be able to handle that in a better way and smoothly. Another consideration is that CRaC represents a stateful approach. It means that the snapshot contains the whole state of the Java application, including the Java heap, which may contain sensitive data, because your application might have written something on the heap before it was paused, right? So you have to take that into account. Then there might be issues with the random. So in this case, you don't use the random class, but instead you use the secure random class, so that random continue being random, actually, after you restore the application. And then the container images are slightly bigger. Well, again, because they contain the Java heap, all right? So that's part of the deal in this case. So to sum up, with CRaC, we have immediate startup, just a few milliseconds, immediate peak performance without warm-up, and the JVM is still there, our favorite Java is still there, so the dynamic performance optimization is still possible. There are all garbage collectors, everything that we love about JVM, that is still there. So that's our good old Java, but, well, with such a mighty feature. The disadvantage is that the snapshot may contain sensitive data. It's only for Linux, and the code refactoring may be required in a bit, but you have to again run your application, see what happens, see what errors come up, and just work it in the individual way. And then finally, there's Project Leyden. Project Leyden is a very, very interesting project because it provides kind of a sweet spot between AppCDS and Graal native image. So, as I already discussed, AppCDS is very simple to use. It's suitable for all applications, but the startup reduction is not really drastic, right? And with GraalVM native image, there are certain limitations, so it may not be suitable for all applications. Then Project Leyden, well, it's kind of somewhere in the middle, and it combines the benefits of both solutions. So the project is focused on selectively shifting and constraining some computations from the production run to some earlier stages, for instance, to the training runs. And selectively means that developers will be able to choose which computations should be shifted and when they should be shifted. It means that it will be applicable to a wider range of applications, right? When you can choose actually what to implement. Project Leyden leverages the power of AppCDS and ahead of time compilation. And it's going to transform the Java code so that it's going to be more performant, right? It's going to start up faster, but it's not going to break the compatibility with the Java specifications. So early access builds of Project Leyden are already available. And here on this slide, you can see what has already been implemented there. Right, so there's one option, cache data store, and when you run your jar file with this option specified, what happens? Well, the ahead of time class loading and linking happens. The ahead of time cache is created. So this cache is going to contain not only the classes data, but also profile data and compiled code. So it's the addition to AppCDS. Ahead of time method profiling also happens. Ahead of time code compilation. Ahead of time generation of dynamic proxies and reflection data. So hello, Java's dynamism. And also the class not found cache is created. Right, so all those things are again very preliminarily, right? So they're subject to change. Some going to be better, I guess, or well, is going to work in another way. So we're going to see that later. But early access builds are not meant for production, so you can use them, experiment with them, play with them, but don't use them in the production. They're not for that. And that's the only disadvantage of Project Leyden that I see at the moment, that it's not yet ready. Right, so the work is being done, right? So the current progress is pretty impressive, and luckily, one feature, so that is ahead of time class loading and linking, is already going to be implemented in the next Java release, that is JDK 24. So this JAP is already there. That's JAP 4.8.3, ahead of time class loading and linking. It differs from AppCDS in a way that AppCDS only reads and parses class data, but this feature is also going to link the classes. So, and that is already an addition to AppCDS, and the startup is already going to be further reduced. You can use Project Leyden builds now, of course, and currently it's super simple to use them. There's only one option, cache data store. When you run your jar file, you specify this option, and then when the application exits, the ahead of time cache is going to be created, and then you run your application again with the same command, so nothing changes. Cache data store, and the JVM is going to read the data from the archive. And I have tried Project Leyden early access builds on my machine, that is Mac M1, and I got a 3 times better startup, which is, well, pretty impressive. Well, to sum up, again, Project Leyden doesn't require any code refactoring. It provides tangible startup and warm time reduction right now and at the early stages of its development. And I believe that more is yet to come, and the startup and warm-up improvement is going to be even more significant. And it is applicable to any application. So again, as I already said, the computations can be chosen by the shifted computation can be chosen by the developer, right? And in the future, if enough computations are going to be shifted and constrained, it might be possible to create fully static images, just like with the GraalVM native image, which is super cool. Oh, the biggest disadvantage is that the project is still under development, right? So we can look forward to it, and we are looking forward to it, but it's not ready for production yet. Another, well, not quite a disadvantage, but consideration is that a training run should simulate the production run as much as possible. So if your application connects to the database, if there are any connections or anything that happens there, it should happen during the training run. Right, so for the project to be able to analyze the application behavior and to yield even better results. And here, finally, we have the actual comparison of startup times. I used Spring Pet Clinic in all cases and JDK 21. All projects, except for Project Leyden, were run in containers. And for GraalVM native image distribution, I used Liberica native image kit. So the container with the application as is, with the default settings, without any optimizations, starts in about 4.5 seconds. The container with the AppCDS and Spring AOT enabled starts in about 3 seconds, which is already an improvement. Project Leyden was tested locally, and the application started in about 1 second. So even better improvement, right? And then the container with a native executable built with Liberica native image kit started in half a second. And then finally, the container with CRaC, so restored from the snapshot, started in several milliseconds. So you can see here the gradual reduction of startup times. And I think it's quite demonstrative of what these solutions do. To sum up my presentation, well, let's discuss some takeaways. So gel applications take time to start up and to warm up. The startup takes several seconds and warm up takes several minutes usually, but it can last for a longer time. That is an issue if you deploy applications to the cloud, because you have to pay for the CPU time, for the cloud resources, and for user dissatisfaction, so to say, because while your service is starting up, it experiences latency, and so the application works slower. Users are not happy. Luckily, there are already existing production-ready approaches. They all have different aspects of their work, right? So, and they are suitable for various use cases, right? So there's never one-size-fits-all solution, but we have, in this case, right now, 3 solutions. So one of them will definitely be your happy side. And as you might have noticed, the greater startup and warm-up time reduction, the greater the challenges of implementing the solution, right? So with AppCDS, it's the simplest one. You don't have to do much to implement it, but the startup production is not very great, and the warm-up production is also not so good, right? And with CRaC, the applications start the fastest, and with native image too. But while you have to take some additional steps to befriend them with your project, right? There are ready container images with all of these solutions, well, except for Project Leyden, obviously. Right, so for instance, Bellsoft provides container images with Liberica JDK Lite, Alpaca Linux, and CDS support, CRaC support, and with Liberica native image kit. Right, so it means that you can take these base images and you can implement the solutions without having to manually set up anything, which is pretty convenient. And finally, AppCDS and native image are supported by build packs. It means that it's just a matter of a couple of lines of code to use them, which is also super convenient. Of course, you can use CRaC with the build packs, but then that's going to be just a little bit more code. So you have to do it manually. Right. So I guess that's all I wanted to say to you today. I know that the topic is not very easy, but I hope I managed to break it down into some understandable parts, and that I hope that it was interesting and useful to you. Well, thank you very much for your attention. You can visit our blog and read more articles on Java performance, on Java security, and new Java features, well, all things Java, basically. There are 4 links to guides that I wrote on implementing each of these solutions. So you can use them and follow the step-by-step tutorials and try these solutions with your project. So the links will be available in the chat or in the description box of this broadcast. And finally, you can connect with me on Twitter or write me an email. Well, again, thank you very much. And if you have any questions, I will be happy to answer them.
Thank you very much, Catherine. This was a very good summary or roundup of Java JVM performance features. Actually, I was reading them all about, but seeing them all together with pros and cons was perfect for me. And as we know, every solution in software development comes with choices and advantages and disadvantages. So these performance solutions are also like that. If anyone has any question, please write in the chat. You can also write in Turkish, so I can translate for you. First of all, I want to ask one question. So these are JVM features, actually not Java specific features. So any developer like Kotlin developers will also benefit from these kind of things, right?
Yes, exactly. So the AppCDS is part of JVM, but Kotlin runs on JVM, right? So you can use it with that too. And yeah, native image and CRaC are well additional solutions that you can implement with your project. I haven't used native image and CRaC with Kotlin because I don't work with Kotlin, but as they work with JVM, then they can be applied to Kotlin code as well.
Yeah. Okay. And another question is, who develops CRaC? I mean, CRaC is not part of JDK, as you said. So it's developed by a third party, or is it a community project?
Yes, it was originally created, developed by Azul, and then Azul contributed to OpenJDK. So it is an OpenJDK project, but it is supported right now by 2 vendors, so Azul and Bellsoft. And if you want to use CRaC, you have to use builds from either Azul or Bellsoft with CRaC support. And if you have any, that's basically a community project in a way. But if you have any questions, you can ask these vendors or in the on forums, and people answer the questions. But yeah, basically Bellsoft and Azul are your go-to people in this case.
Oh, yeah. And my last question. I remember I saw that AWS Lambda uses CRaC behind the scenes to increase the startup time, because, as you said, it dramatically increases the startup time. Do you have any statistics or usage data about that? How is it on AWS?
I don't have official statistics, but I communicated with some people from Google. So Google also has Google functions that are just like AWS Lambdas. And I know that developers are more and more interested in CRaC and in native image. So these technologies, the popularity of these technologies grows actually. Yeah, so people start implementing them because they enable you to use AWS Lambdas and Google functions, right? Because without them, it's pretty useless, right? To try and run Java with AWS Lambdas, that's, well, quite impossible.
Yeah,
It's possible, but
right.
it's not very convenient. Yeah.
Okay. So another question from İsa Güler. Do features such as CDS, AOT, and CRaC enhance runtime performance or optimize memory usage? Or are their benefits limited to improving startup times and reducing image sizes?
Great question. Thank you so much. So yeah, that's that's actually really very good question, because in the beginning in my presentation I talked that startup is not the only problem. Another problem is that the memory overhead, right, during the warm up. And so with AppCDS, it doesn't actually influence much the memory usage, right? Because it doesn't influence much the warm up times. The only situation where AppCDS can decrease the memory usage overall is when multiple JVM processes use the same archive, right? And then, yeah, the memory usage is reduced. But not in case of Warmup. With the native image and with the CRaC, the situation is quite different. And I have some data, so I run tests, and they not only reduce startup, but also the memory usage is much, much smaller than with the traditional application or with application that runs on AppCDS. This is because there's actually no warm-up, right? So the application starts already at peak performance, and so it consumes less memory. So yes, by using a native image or CRaC, you will be able to reduce the memory footprint of your applications.
One last question from Furkan. Actually, Bellsoft is a technology developing company. Does Bellsoft have a career page? What kind of technical questions are asked during recruitment? And what do you expect candidates to know? Actually, a representative from Bellsoft answered this question on chat, but we wanted to hear from you as well.
Yes, well, we are a technical company, yes, and we are extending ourselves, right? So we are always looking for engineers, and as far as the career management, the vacancies are posted, I guess, on LinkedIn. As far as the career page, I guess it's under development, so maybe it's going to be ready. But if you want to work for Bellsoft, you can write to us, connect with us on LinkedIn, for instance, and then we'll see what we can do.
Yeah, of course, you have to be very in-depth knowledge about OpenJDK, because it's a JDK company.
Oh yeah, so actually that's very deep rooted in JDK, because our flagship product is Liberica JDK. So yes, you have to know the JVM world as your own, right? And Linux, so we develop Alpaca Linux. Then yeah, the expertise in Linux is also obligatory. Well, depends on the project that you want to work on.
I think that's all for the questions. Once again, that was a very inspiring talk, and I benefit, and I think everybody benefited very much from it very much. So once again, thank you for our sponsor, Definex, and thank you for all the people supporting us. Don't forget to like and subscribe to our channels. And it was very pleasure to host you in our channel today, Catherine.
Yeah, it was just great. Thank you so much, Mustafa. Thank you guys for visiting, for listening to the presentation. I hope this is not our last meeting here, and that we're going to make something fun somewhere in the nearest future. Right. Yeah. So thank you so much. It was a pleasure. Thanks.